continue with section 7.1, and we're going to talk about applications because this is one application where, or one set of equations where there are lots of applications that actually are relatively easy to look at. This exponential growth model that I have written down here, this I want you to have in your notes. So I'm going to give you a minute to write that down, and when you've got it written down, I want you to open up your textbook to page 480, and we're going to look at example 4 because I didn't want to write all of that out, but I want you to look at that. We're going to talk about how to write an equation that fits that set of criteria. So whose flag you got on?
Sweden. Pittsburgh tennis. It's the league. The league.
Okay, while you're finishing up, I'm going to talk about a little bit what it tells you here. The exponential growth model is of the form y equals constant a times 1 plus r raised to the t power. That a is always the initial value. Now, if you think about it for a minute, that should make sense, because if I'm starting when time equals 0, then this 1 plus r to the 0 is going to be 1. So when t equals 0, then y is a. So that's my starting place. Okay? My r is whatever the percent increase is. So let's talk a minute about when this formula, this model, is applicable. This model applies anytime you have an approximate increase, percent increase that is the same year after year or month after month. So actually, when you see models that say, or you see statements that say things like, in the year 2050, this is going to be the population of the Earth. This is the kind of model that they use, because they say, okay, the percent increase, the population is increasing by whatever it is, 5% a year, 2% a year, and they create this kind of a model. Now, obviously, you're looking at the population of the entire Earth. It's not going to be this simple of a model, but this is the idea. This is how they approach those kind of things. If you look at all of the part inside the parentheses, I take 1 plus r. That's called the growth factor. And our t is in time. And time can be measured in whatever length of time your percent increase is over. If it's this much of a percent increase every month, then t would be measured in months. If it's this much of a percent increase every second, say I'm looking at a bacterial colony, then t would be measured in seconds. Okay, so it's going to depend on your problem. So let's look at, we're going to look at computer viruses on page 480. Do I have any volunteers to read? Okay, you'd rather listen to me? Okay, I'll read it. You read along with me. In 1996, there were 2,573 computer viruses and other computer security incidents. During the next 7 years, the number of incidents increased by about 92% each year. So that last statement tells you that this is indeed an exponential growth model, because it says it increased 92% each year. So function, they told us to use n instead of y. So we're going to replace, so y we're going to replace with n in our little formula. And that's going to represent the number of security incidents. There we go. Okay. What was my initial value? 2573. That's how many we started with. Okay. What's my R going to be? 92%. So I have R equals 92%. Now, we aren't going to write it just as 92. We're going to write it as a decimal. So you remember that 92% is 92 divided by 100. So I move my decimal 2 places to the left. So that's 0.92. The growth factor, we're going to figure in a minute. We don't have to actually identify that one. So my time, and t is time, that's going to be one of my variables. So I'm ready to write my equation. So I'm going to say n equals, okay, my a is 2573, 1 plus 0.92 raised to the t power. Or in a simplified version, I would say n equals 2573 times 1.92 to the t power. And remember, the 2573 isn't raised to the t power; it's just the just the growth factor. So 1.92 would be my growth factor. So there's my, now that when we talk about write a model, that's what we're doing. We're going to write that equation. You just wrote the model. Okay? Now, let's use that model a little bit. So I've got this graphed already, and hopefully you brought your calculators, because I'm going to have you graph them as well. There it is. Turn that off for a minute. Looks something like that, which looks like all of our exponential functions. Now, when you graph it on your calculator, it's not going to look like that just yet until you adjust your window. Here's my window that I used. I said x min would be 0, x max up to 10. That's years. They'll think about the x's instead of the t. Now my y, I started at 0, and I went up to 140,000. So you have to kind of play with the windows when you're dealing with more real world type applications. They don't necessarily give you nice, easy numbers to work with. Now, got some other stuff written up here, but we'll get to that in a minute. Everybody get it graphed? Kind of like that? We're good? You okay, Lauren? Okay. I'll give you a minute to get that put in. Now, the next question on this particular example says, find how long, estimate how, when there'll be 125,000 computer security incidents. So I need to use my graph to estimate when this is going to get to 125,000. Well, one thing you can do, if I do a trace on here, we got 0, 2573. That's what we picked it that way, right? Okay, so as my time increases, I get up to 1, and it's increased a little. Let's see, 2, it's increased a little bit, 9673. I go up to, let's say, 4. There's 4 there. And it's about 35,000, so it gets pretty big pretty fast. That's that exponential growth. Now, when I go up to 5, what happens? I get up to, Where's 5? There's 5. 67,000. So now I want to know how long is it going to take to get to 125,000. So what you're going to do in your Y2 in your calculator, you're going to graph Y equals 125,000. So this is what we do when we know a Y value and we need to find an X value. Do you guys remember how to do the intersect feature on your calculator? Yep. So you should be able to do the intersect feature on your calculator, which I have it written down here if you can't remember. You say second trace, get to the calculate menu. Number 5 says intersect. Now we only have 2 curves here. So it asks first curve, and usually it does Y1 first. You say enter because we want that one. Second curve, Y2 next, so you push enter. Yes, we only have 1 intersection, so we don't need to worry about that. So push enter, and you should get X equals 5.953, and then comma 125,000 for your Y. So that's how, if we know the Y value, that's how we can figure out the X value. If I know the X value, guys, if I know how much time it was, we put T in for your X, whatever that time is, and that's going to get you out of Y. You guys know how to do that. Okay, so that's how you would use one of those models. Any questions about that? Now, let me get back to this. This equation, Y equals A times 1 plus R to the T, I expect you to know that one. That one's one you need to learn, memorize, whatever. If I ask you to write the model on the test, you need to be able to do that. Okay, so fair warning on that one. Also, the decay model you're going to learn on Thursday.
Equation and what all those letters mean.
Yeah. Well, I probably won't have you write out what all those letters mean, but you better know how to use them. Okay. So, now, I've got a second one, and this one I won't ask you to memorize. I will give you the formula. I probably won't give you all of the list of what they all mean, but I will give you the formula. The compound interest formula reads like this. A equals P times 1 plus R over N raised to the NT. It's pretty similar to the one you just had. That N kind of throws a little wrinkle in it. How many of you know what compound interest is? Yes? Yes, a little bit maybe. You know what interest means, right? If I put money into my savings account, let's say that's what this is over here. If I put $100 in my savings account, and nobody gets 10% interest now, but it's a nice easy percent to work with. If I was earning 10% annual percentage rate, you take, at the end of the year, you take 10 times 0.1, I'd have $10 in interest. They add that to my account, now I have $110, the way interest works, okay? Now, if it's simple interest, if I left it in there for 5 years, you just take this times 5, and I'd earn $50. If it's compound interest, you have to, every time you figure the interest, you compound it, you add back in the interest you earned, and you actually figure your percent of the entire amount to get your interest earned. So in year 2, if I had $110, you take that times 0.1, and I'd earn $11 instead of $10. And now I would have $121 instead of just $120. That's how compound interest works. Okay. So you can see, hopefully, if I had to do that every time I wanted to figure out in 20 years, and it's compounded 4 times a year, I'd have to figure it 80 times to figure out the correct answer. How much money I'd have at the end of that length of time. But that's why we have this nifty little formula to figure that out for us. We don't have to do it one item at a time. So, here are my formula. A is the amount in your account at any given time. P is your initial investment. That stands for principal. That's whatever you put into the account at a given time. R is the percent annual interest, and that's why we have the N, because the N is the number of times it's compounded annually. So if my R is the percent annual interest, and I'm just figuring my interest once a year, N is 1, and it doesn't look any different than the last one we had. But let's say it's compounded quarterly. How many times a year is that? Four times a year. So that means I only get to use my interest rate divided by 4 for that 3 months. And then I'm raising my time, since time is measured in years, that means I'm going to have 4 times during the year instead of just once. So that's where the little change in the formula comes in. And then time in this formula is always measured in years. The other one, it can vary with the problem. This one's always years. Okay, so let's look at an example. I deposit $4,000 in an account at 2.92% interest, annual interest, and I want to know at the end of 1 year how much I would have in my account if it was compounded quarterly. And then I'm going to do the second one for a date. Okay. 4,000 is going to replace what variable in my formula? B. Okay, so 4,000 is B. What's this one going to be? That's going to be R. And we're going to write it as a decimal. So I'm going to move 2 places to the left. So that's going to be 0.0292. 1 year. That's T. So quarterly, that's going to tell me that M equals 4. Daily, we're going to do that one in a separate problem. Then how many days in a year? 365, and you assume that it is not a leap year. So you just use 365. Okay. So let's figure it out. So you're gonna now when you do your problems, for every one you do, you're gonna write this out. A equals 4,000 times 1 plus R is 0.0292 over 4 raised to the 4 times 1. So for every problem you do, I want to see that written out like that. Now you don't have to show the steps of figuring this out. At this point, you get to grab a calculator and figure it out. So I want you to do this with me so you make sure everybody gets the same answer I do. Now, you can do it just the way it is with parentheses. I usually do it, and I find I get more accuracy if I work from the inside out. So here, I'll tell you the way I do it. I start with this division problem in the middle. So I would say 0.0292 divided by 4, enter. 0.0073. I'm going to add 1. So I say plus 1, enter. I'm going to raise all that to the 4th power. So raise to 4th, enter. I got 1.0295 and so on. And now I take all of that times 4,000. And I get, remember to use your dollar sign for your answer, $4,118.09. And since we're talking about money, we're going to round to the nearest cent. And anytime you have money, unless it tells you otherwise, round to the nearest cent. Okay, everybody good? We got that? Okay, let's do the same thing for daily. Would you expect this to be more or less? More. You're compounding more often. So let's see if it is. So you're going to write down A equals 4,000 times 1 plus 0.0292 all over 365, and that's going to be raised to the 365 point. Okay, I'm not going to tell you the steps here. I'm just going to do it. something a little more. Not very much. $4,118.52. I guess you do need to round that correctly. So it's a matter of a few cents, but over time that gets bigger. Or if you had a bigger investment, say it was $40,000 instead, or depending if it's your retirement account, that's probably going to be bigger than that. Someday you'll have one of those. Okay, so this is how this works. Any questions? It's a matter of applying the formula, plugging in the numbers. Okay, so that's going to be the first part of your worksheet. I've got another example, but I'm going to skip that. I think we probably got this. I got one more thing I need to show you. Okay. Question is, you're going to invest some money at 7% compounded annually. How long is it going to take to triple your money? I'm going to write our formula down again. What do you think? 4 years? 42 years. Okay. Okay, we'll see how you do. What do I know here? I know R. That's 0.07. What else do I know? Okay. N equals what? Annually, how many times a year? That's once. Okay. So N equals 1. Now T is what I'm looking for, right? Time, how long? That's all it tells me except for the triple your money part. So here's what we're going to do. If I invest $P, when I triple my money, how much is my amount going to be? 3P, right? Take 3 times what I invested, it's triple now. That makes sense? Okay, so let's fill in what we got. So we got 3P equals T times 1 plus 0.07 over 1 to the 1 times T. Okay, let's simplify this a little bit. I can divide both sides of my equation by P. And now I have 3 equals, well, the dividing by 1 makes life pretty easy. So that's 1.07. And T times 1, that's just raised to the T's out. Now, when we finish this section, we're going to talk about logarithms, and we're going to have a way to solve this directly. But right now, we haven't talked about them, so we're going to do a little guess and check. You thought 42 years, so let's try and see what that gets. I take 1.07 to the 42.
Just randomly. Yeah.
42. I get 17. Because that would take my money times 17. So that's longer than I need. Another guess. How long do you think it might be, guys? 8? Okay. Let's try 8. That gives me 1.7. So not quite enough there. So somewhere between 8 and 42.
13.
13. I like that guess better.
No.
Okay, 1.07 raised to the 13.
I say 15.
Okay, 2.4. So let's try 15.
20. No, that's not 20. Sure.
That's
15 is 2.8, so we're pretty close.
16.
1.07
Fine,
to
fine, sir.
16.
it's yeah.
If you keep me rounding up, it'll be great.
2.95. We haven't quite reached 3 yet.
But it's closer to
17
16.
years. Well, yeah, 3.1.
That's 15 off. 15 cents off. Now
3.2.
5 off.
Okay, 3.16. Now, have you tripled it yet at the end of 16 years? No, so you have to go to 17.
But then you're throwing the extra 5 cents that your grandma just gave you, and boom.
That's right, well, you. For our purposes, we're gonna say about 17 years. Now, when we learn logarithms, we'll get much more precise, and I'll make you do it to the decimal value. But right now, this is close enough. Okay? So that's what I've got for you today.